Hey everyone, welcome to The Explainer. I am absolutely thrilled you're joining me today because we're looking at a truly fascinating and honestly slightly terrifying piece of research. We are pulling apart a paper called Noisy Covariance Matrices and Portfolio Optimization by statistical mechanics researchers Pafka and Kondor. Our main goal today, we're going to figure out how massive amounts of random, unpredictable noise actually impact the complex mathematical models that institutions use globally to manage our money. I mean, imagine relying on a compass to navigate this treacherous financial ocean, only to find out the magnetic field is constantly flickering. Because as you'll see, that's essentially what we're looking at today.
Okay, let's start right off the bat with a number that honestly blew my mind: 94%. When these researchers looked at empirical covariance matrices deduced from financial return series, which is basically just the historical data matrices used to predict how different assets move in relation to one another, they found something staggering. About 94% of the spectrum of these matrices is essentially just random noise. Just think about that for a second. The massive models protecting billions of dollars are feeding on data where 94% of the mathematical structure could literally be swapped out with a purely random matrix, and it would look the exact same. It's kind of like building a skyscraper and realizing 94% of your concrete is just sand.
Okay, let's really dive into this because breaking down the math drives the point home perfectly. A massive 94% of the data is just noise. It's chaotic, unhelpful, random data points that tell us absolutely nothing about future financial risk. That tiny remaining sliver, just 6%, represents the stable, large eigenvalues. We can think of those as our structural anchors. In data science terms, that little 6% slice is the actual signal. It's the only meaningful structure in the market data. So the immediate burning question we have to ask is, how on earth does modern finance survive on just a 6% signal? So here's our roadmap for this explainer. 1. The core tool. 2. The setup. Is the model broken? 3. World 1. The safe zone. 4. World 2. Serious instability. And finally, 5. The big takeaway.
All right, let's jump right into part 1, the core tool, understanding the foundation. Now we're talking about covariance matrices. And I know these aren't just abstract blackboard mathematical concepts. They are deduced from financial return series, and they are the absolute fundamental bedrock of portfolio optimization. Whenever a major firm is out there trying to balance risk and reward, deciding how much stock A to hold versus bond B so that a crash in one doesn't wipe out the whole portfolio, they are relying on covariance matrices. They're the backbone of industry-wide risk management practices. If the matrix is flawed, the entire foundation of a portfolio's safety is totally compromised.
Which brings us to part 2, the setup. Is the model broken?
Right, so if 94% of the data is random noise, does it completely break these crucial financial models? That is exactly the question researchers Pafka and Kondor set out to answer. Because given the fundamental role these matrices play, having 94% noise sounds like an absolute catastrophe waiting to happen. So they ran these extensive simulation experiments using matrices structured to mimic this overwhelming noise to see the actual implications for portfolio optimization. They really wanted to see if the industry's compass was completely shattered. And what they found was this fascinating tale of two completely different mathematical worlds.
Let's look at their first finding in part 3, World 1, the safe zone.
So defining this first world, the researchers looked at what happens to the classical portfolio problem. Now in financial theory, this is the traditional approach where you are trying to minimize the portfolio's variance, or basically its risk, under linear constraints. Linear constraints are just simple straight-line rules. For example, a rule like the sum of all my investments must equal 100% of my capital, or I want exactly a 5% expected return. These are straightforward linear equations.
Now, what's really interesting here, and honestly super counterintuitive, is that in this classical linear world, that massive wave of noise actually has very little effect. No way, right? How is that even possible? Well, to the leading order, the mathematical solutions are determined almost entirely by that tiny 6% slice we talked about earlier. Those stable, large eigenvalues are structural anchors. The math of linear constraints inherently locks onto the strongest signals and essentially ignores the vast sea of random noise. It's kind of like you're at a definitely loud rock concert, but your brain somehow manages to perfectly tune out the entire crowd and hear only the lead singer.
Now, obviously it's not totally flawless. The noise does push the solution slightly off course. The researchers measured this displacement in terms of variance and found that, depending on the size of the portfolio and the length of the time series you're looking at, the displacement is generally between 5 to 15%.
So yeah, the optimal portfolio isn't perfectly optimal, it's shifted by up to 15%. But in the grand scheme of things, considering 94% of the data is garbage, a maximum 15% displacement is an incredibly robust, safe outcome. The classical model actually survives.
But then, things take a major turn. Part 4, World 2, Serious Instability.
So we just saw that under linear constraints, everything is mostly fine. But the researchers noted that the picture is completely different if we attempt to minimize the variance under nonlinear constraints. Nonlinear constraints are much more complex rules, where the variables actually interact with each other, curving and amplifying in totally unpredictable ways. And when you shift the math from linear to nonlinear, you completely strip away that natural defense mechanism we just talked about. The model can't just focus on the lead singer anymore. The deafening roar of that 94% noise floods the entire system.
And this brilliantly illustrates why this paper is an absolute must-read. We aren't just doing abstract math for fun here. Real-world financial systems heavily rely on nonlinear problems. Two massive examples the researchers cite are the calculations required for margin accounts, which is where investors borrow money against their current assets to make larger trades, and international capital adequacy regulations. These are the actual global banking rules designed to ensure banks hold enough capital to survive massive economic shocks. And those rules, they are profoundly nonlinear.
I actually want to read this direct quote from Pafka and Kondor, because it really hits the nail on the head. In these problems, the presence of noise leads to a serious instability and a high degree of degeneracy of the solutions. Degeneracy. Instability. When you mix that 94% data noise with nonlinear financial regulations, the math simply falls apart. The solutions become wildly unstable, meaning a tiny change in the market data could spit out a radically different risk assessment for a global bank. The compass doesn't just flicker anymore. It spins violently out of control.
All right, wrapping it all up. Part 5, the big takeaway.
So the crucial point reveals a dual reality in financial modeling when dealing with noisy empirical covariance matrices. It's a tale of two worlds. If you're operating under linear classical constraints, you're largely protected. Sure, you'll see a minor variance displacement of 5 to 15%, but the model holds up. However, the exact moment you step into the modern regulatory and trading environment of nonlinear constraints, like calculating margin risk or international banking capital buffers, that 94% noise triggers serious instability and mathematical degeneration. The exact same tool that works perfectly in one environment becomes a highly dangerous liability in the other.
Which leaves us with this final massive question. If 94% of financial covariance's data is noise, and nonlinear systems degenerate in the presence of that noise, how can we implicitly trust the international capital adequacy regulations that govern our entire global banking system? Are the safety nets protecting our global economy literally built on mathematical structures profoundly vulnerable to the very data they consume? It's kind of a chilling thought to walk away with today, right? Well, thank you so much for joining me for this explainer. Keep asking those hard questions, and I'll catch you next time as we decode more of the world's most fascinating research together.